The solution to the harmonic equation is one that you'll learn how to derive in a differential equations class. Here we're less interested in deriving that solution, but rather going right to it and using it. Right? So since v is our symbol for our function here, then our solution for this differential equation is going to be v of x is equal to a times sine of cx plus b times cosine of cx. Note that in the expression you see a c squared here, and so the argument in the sine and the cosine functions is going to be the square root of that c, and so you get this little nice thing that we had before, that we had established that c squared was equal to p critical over ei. And so we got to figure out here how to deal with what turns out to actually be 3 constants, and yet we only have really 2 conditions associated with the displacement, and that's of course these boundary conditions. Right, so let's look at the boundary condition at 0. That would be up at the top, this pin-end system, right? And it has then a 0 displacement there, right? It's not moving perpendicular to the long axis. And so now when we substitute in for 0, what we're going to get is, for x is 0, we'll have a times sine of c times 0 plus b times cosine of c times 0 is going to have to be equal to 0. Well, cosine of 0 is 1, and sine of 0 is 0. So that just is going to tell us that our second constant, b, is itself 0. Now that might seem like a problem because we're starting to get a lot of zeros popping up here, and that means a trivial solution, which we don't want. That's not going to help us any. But we still have the first term left over, and we have one more boundary condition out there at the bottom of our system, which also at length L would have a transverse displacement that would be equal to 0. So we won't include the second term anymore because b is 0. We just have a times sine of c times L is equal to 0. Well, a cannot be equal to 0 because otherwise we do get the trivial answer. And so therefore that means sine of CL has to be equal to 0. And that happens only at specific locations, right? That CL has to be equal to n times pi, where n, you could say n equals 0 would be a possible solution, but again, if n equals 0, it's a trivial answer. So n equal to 1, 2, 3 integer values of pi as we work our way up. That c, wow, well now look at this. That means that c squared is equal to n squared pi squared over L squared. But we also know that c squared is equal to the critical load divided by EI. And there you have it. We have our base model then for our critical load, which is that it's equal to n squared pi squared times EI over L squared. Now that might be the end of it, but wait a minute, what's the value of n supposed to be? Well, consider that n equal 1, 2, 3, all the way up to infinity would be all possible answers, right? But as n gets larger, the whole critical load value, the buckling load, would also get larger. But this is sort of a weakest link thing, right? You don't start with loads on a system that are super large and get smaller. You start with an unloaded system that gets then more severely loaded as you increase the applied loads, right? And so the first time we reach the critical value, the lowest one will be n equal to 1 in general. And we'll see later on how you can get some of these higher modes that we call it. But the basic Euler or critical elastic buckling load would be at n equal to 1. So that would be P sub E equals pi squared EI over the length squared. Now, Real columns will behave slightly different than this, and we'll talk about that in upcoming video segments.